Let's go ahead and introduce our speaker for today. So we are very happy to welcome Amy Braverman as our October STEMS webinar speaker. So Amy is a principal statistician at the Jet Propulsion Laboratory, which is a NASA research center in California, operated by Caltech. And JPL, it's famous as the place that builds and operates the NASA Mars rovers, but it's also the place that builds and operates a lot of the NASA Earth science satellites. And those missions involve a lot of non-trivial statistical challenges, and Amy is effectively leading a lot of the efforts to find solutions to the statistical challenges that NASA is faced with in their Earth science missions. She holds a PhD in statistics from UCLA, and her research interests include massive data analysis, space-line space-time approach statistics, data fusion, decision-making in complex systems, and answering quantification. And especially on the last topic of answering quantification, she has been leading a lot of recent efforts on answering quantification for remote sensing, both at NASA and beyond. That's also what she will be talking to us today about. So the title of her talk is Post-hoc Answering Quantification for Remote Sensing Observing Systems. With that, Amy, please take it away.
Thank you, Mikhail, and thank you to the organizers of STAMPS for inviting me to talk. This is not quite as good as coming to Carnegie Mellon, which had been on the table at one point, but maybe I'll get to do that yet. Who knows? Anyway, thanks, Mikhail. I'd like to thank my co-authors, John Hobbs, Joachim Teixeira, and Mike Gunson, all from JPL, for the work that they did on this project. This was really a collaboration amongst all of us. Here's my, oops, I have to make it, there we go. Here's my, the outline of the talk. It's the usual sort of thing. I'm gonna introduce the problem a little bit, talk about remote sensing observing systems, tell you a little bit about the Orbiting Carbon Observatory 2 mission. That was the motivating application for this work. I will put it in something of a statistical context and connect it to some notions of uncertainty quantification from that community. And then I'll talk to you about methodology and show you some results, and then we can talk about it at the end. For those of you that may have seen this talk before, I hope you enjoy the rerun version. Okay. As you may or may not know, when NASA or any other space agency puts an Earth observing or a Mars observing satellite into orbit around the planet, all those instruments do is measure photon counts in different bands of the electromagnetic spectrum. So when one talks about NASA data products, something like surface temperature, it's not like there's a big thermometer up there in space that is somehow magically able to see the surface of the Earth and measure the temperature directly. Those sorts of geophysical data are inferred from these raw photon counts from the satellite. And NASA, and I think ESA too, likes to talk about levels of data processing, where the photon counts in each different spectral band are sent down to Earth. And then there's a lot of processing that happens. The first thing is that level 0 data is converted to what's called level 1 data, which are geo-rectified and calibrated radiances, meaning every datum that belongs to a given pixel in the scene is given a spatial location, and it's calibrated to make it directly comparable to the other radiance counts in other spectral bands that are on the same instrument and looking at the same place on the ground. And it's only in going from this level 1 to level 2 that there's estimates of geophysical state, like surface temperature or temperature in the atmosphere or water vapor in the atmosphere or cloudiness or properties of the surface or properties of the ocean, like ocean height or sea surface temperature. Only then are the geophysical states inferred from level 2. Inferred at level 2. To complete the picture, quite some time back, NASA decided that all missions would provide something called level 3, which are, quote, statistical summaries, unquote, of level 2 on a uniform space-time grid. This is typically done by cutting the Earth up into little latitude, longitude squares and populating each of those squares or cells with the mean of each quantity of interest and maybe its standard deviation. Finally, level 3 and sometimes level 2 directly are used as the input to models or to a data assimilation in order to draw even higher level inferences from the data that we have and the models that we have. But my point here is that in going from level 1 to level 2, these data aren't data the way a statistician thinks of data. They're inferred from something else. So they are inferred from the observed spectra. And here is a cartoon of what that process might look like, just to establish some terminology. My own face is blocking the right side here, so I'm going to move that a little bit out of the way. What you see here going from left to right is my notional cartoon of a remote sensing observing system. The things in gray are things we do not get to know, and the things in blue are things we do get to know. Starting on the left, we start with a true state at some location and time, and it's likely a state vector. And nature has something called a forward function, which governs how that state transforms photons that come in from the sun and scatters them back out in the direction of the spacecraft. That produces something called a noiseless radiance, which, adding measurement error epsilon to that noiseless radiance, produces what the spacecraft would actually see, which we'll call the observation. So typically, a true state vector is something like a column profile of carbon dioxide concentrations or the amount of aerosols in the atmosphere, or more likely both of those things together, a description of the physical state of the atmosphere or the surface. Nature's forward function I'm going to call F0, and it ingests F and spits out Y0, which is this noiseless radiance. And we talk about nature's forward function depending on certain parameters, which I'll call capital B0, which are also unknown, right? So X is unknown, F0 is unknown, B0 is unknown. Technically, Y0 is unknown. Epsilon, we have some idea of what its statistical properties are from calibration in the laboratory beforehand. So we think we know what the distribution of epsilon is, but really all we get to see are the things in blue on the right. Now that radiance vector, Y, the spectra, are pumped into a big computational system called a retrieval algorithm. The word retrieval comes from the fact that we try to retrieve or infer the true state of the atmosphere from this noisy observation Y. And in doing that, it involves essentially using our best guess at what F0 is, which I'm going to call F1, and its corresponding parameters B1, to try to, let's say, choose from different possible true states that might have given rise to Y, the observation. And we call that state estimate, which minimizes some cost function, X hat. So the retrieval is an inference problem where you want to estimate the state when you only get to see the radiance. I've also put dots in there to indicate that there are other things that affect that retrieval that we're not even going to, we may not even be able to completely identify, like computational artifacts, unknown unknowns, and the like. Whoops, back here. Okay, so just one quick word about uncertainty quantification, which has become an extremely popular topic. I'm sort of self-taught in this area. I've had the advantage of being at JPL, where I could talk to a lot of people about it. And I've had a lot of good conversations with people outside of JPL who know more than I do. But I got this graphic from the paper that's referred to down below. And I thought it was kind of a nice description of what the discipline of uncertainty quantification kind of looks like. Actually, uncertainty quantification often is referred to as VVUQ for verification, validation, and uncertainty quantification. The aim of uncertainty quantification typically is to assess the reliability of predictions of complex computer models, like, let's say, computer code over there in the corner. There's something called forward UQ, which you could think of as if you had an ensemble of inputs to that computer code and you ran them all through the computer code, and then you got an ensemble of corresponding outputs, how well does that ensemble of corresponding outputs compare to reality? That's what the validation effort is. Now, in the course of getting a hold of that ensemble of potential inputs, you would need to know the distribution on those inputs, or the input uncertainty. And a lot of times there are certainly quantities that go into your computer code whose distribution you have no idea about. So there's this idea of something called inverse UQ, where you sort of work with what you know from reality, from your experiments on the ground, and the output of your computer code to try to understand what the input distribution ought to look like. And often this is an iterative procedure where you kind of bop back and forth between your forward UQ and your inverse UQ and trying to hone in on the answer to both of those things. So I bring this up because you might be wondering, what in this context is the computer code that we would be evaluating? When I go back to this, I'd like to point out that it seems natural that the computer code could be the retrieval. That's a big computational model. But in what we're looking at here, I would assert that the system that's being evaluated is not only the retrieval, it's actually the entire flow of the observing system, starting from the true state all the way to the end. And I'll try to make that a little bit clearer as we go on. So that maps in different ways to different boxes or ellipses on this, on here. If I put the retrieval code here, then the input is Y, and I need to know something about the input uncertainty. And I have very, very little experimental data to compare to. I have only a few ground stations to compare to. An alternative would be to consider that the computer code of interest is actually the forward model, and infer the true state that led to that through this inverse UQ procedure. But I won't dwell on that. I could probably spend the rest of the time talking about it, but I won't. You'll see what I mean later. So uncertainty quantification provides a formalism for understanding uncertainty in the output of complex computational models. Remote sensing data obviously utilizes complex computational models, but there are a lot of things we don't know when it comes to remote sensing that in more traditional uncertainty quantification settings we do know. For example, there are a lot of uncertainty quantifications in the engineering domain where physical equations govern the stresses or the loads on I-beams in skyscrapers and things like that, where we have a pretty good idea what the physics are. And we have a pretty good idea about most of the inputs into our model. Here, we lack information about the uncertainty of our inputs. There are many unknown unknowns. In fact, we don't know really how many interaction effects there might be among the different things that go in, and we don't even know if we're missing something that should be an input to the model. Computational artifacts must be taken into account. A lot of these retrieval algorithms rely on convergence to global minimum, but that can't be verified, and they're known to be trapped in local minima, and that can cause artifacts. And another problem in our setting is that we were asked to formulate a strategy to do uncertainty quantification for the Orbiting Carbon Observatory 2 mission, but the thing was already flying and the retrieval algorithms were already in place, and we are not allowed to change anything about how those computations are done. We can only do something with it after the fact. So that was our challenge. Now I'll tell you a little bit about OCO2. OCO2 was launched in 2014, and it's been up for 6 years now, collecting a wonderful record of total column carbon dioxide concentrations in the atmosphere at very fine spatial resolution, about 1 kilometer. The science question that's at issue here is that there's this, we speak of carbon sources and carbon sinks. Carbon is exchanged between the surface and the atmosphere. A carbon that goes from the surface to the atmosphere is called a source, and carbon that comes out of the atmosphere and is, let's say, drawn into plants or into the ocean is called a sink. But it's not known how to close the carbon budget. It seems that there's a missing sink somewhere, but no one really knows where it is or how it works. I think some people suspect it's in the Indonesian rainforests, but we would have to ask a real scientist about that. So these are some of the questions that we have about CO2. How will climate change affect the rate of uptake, and how will anthropogenic emissions affect the injection of more carbon into the atmosphere, and how will all that interact with the climate system. So let me move here. Here's another picture of what's going on there. As I said, a primary objective of OCO2 is to find and study natural sinks. Prior to the space-based remote sensing era, there were field campaigns at various places around the world where people instrumented towers on the ground to measure carbon dioxide concentrations, but it's a whole new world with global observing systems like OCO2. The challenge here is to get high precision estimates of carbon dioxide concentration that result from small changes in flux with large natural background variations. So if we're looking for example, see this little factory over here. This is 6.4 in whatever these units are in here. It looks like gigatons per year of carbon. That's 6.4 compared to ocean sources and sinks on the magnitude of 70, 20. The land sink, the source of the gross primary production, plant respiration at the level of about 120 gigatons. So it's hard to see these changes, and it requires a very, very accurate measurement system. All right, just a little bit more about the OCO2 observing strategy. Over here on the left, OCO2 is in polar orbit, which means it flies around the Earth from north to south, or south to north, if you like. It completes between 14 and 15 orbits a day. It's got a very narrow swath that is only about 10 kilometers wide. So every time the spacecraft goes around the Earth is moving underneath it, and you get this sort of basketball-like pattern of the ground tracks. The measurement principle is that photons from the sun pass through the atmosphere. They are absorbed and scattered by different constituents in the atmosphere, including CO2. It bounces off the surface, heads back up to the spacecraft, and it gets focused onto a detector shown in the third panel here. And the upshot of that is that you get a ground footprint that looks like this area, this thing on the left. Each of these little parallelograms are 1.29 kilometers by 2.25 kilometers in size. And for every one of those little ground footprints, you get a vector that is, with some caveats, 3,048 different photon counts for that vector of radiance as y. The state vector that we presume gave rise to that radiance vector is a 45 by 1 atmospheric state vector x, which includes the CO2 dry air mole fraction at 20 altitudes and a bunch of other descriptors of the properties of the atmosphere and the surface, including aerosol types, the albedo of the surface, which is its reflectivity, and various other things. I'm going to keep my eye on the time here. The retrieval is somewhat underdetermined. So the team has decided that the actual data product that will be reported, remember I called that X hat, which is our estimate of, bold X hat here, which is our estimate, a posterior estimate of the state vector. We use, the OCO2 uses a retrieval methodology called optimal estimation, which is basically a computational implementation of Bayes' rule to try to estimate X hat, which is the state vector given the radiances y. Remember that I said that there are 20 elements of that state vector that correspond to altitudes of carbon dioxide concentration at various different altitudes. And what is actually reported in the product is a single scalar value per pixel that we call not bold X hat, which is just a weighted average of the carbon dioxide elements of the state vector. That's a much more robust quantity than the profile itself, and it is sufficient for input to data assimilation algorithms that would then subsequently estimate the flux. So what we get is we get an estimate of, we get a point estimate X hat, which is the expectation of this quantity, and there's sort of a crude estimate of the variability of the total column concentration of XCO2, which is called XCO2, by the way, which is computed essentially as a linear function of X hat. So what can I tell you? The way that the OE algorithm works is it searches for a map estimate of a penalized cost function that can be interpreted as a Bayesian cost function that has a portion of it that's just the squared distance between the predicted radiance and the observed one, with a second term that basically functionally puts in a prior. And the prior is chosen by scientific knowledge based on the expertise of the people on the team. For inferential purposes, however, there is the strong, if not explicit, suggestion that everything in sight is Gaussian. And X hat is in practice treated as the posterior mean of XCO2, and S hat is treated as the posterior variance of XCO2. So here's our flow again. This time I've ungrade everything. And I wanted to point out a couple of things. It's our perspective that the system, the observing system, actually runs from the left side of my diagram all the way to the right side. And while I can't know what's going on exactly in the left side of my diagram, I can ask what the properties of this system are. What happens between the time when X goes in and X hat comes out? And I can think of that as a big statistical experiment in which I have a sampling strategy that's governed by the instrument's observation scheme and an estimator, which is in fact encoded by the retrieval algorithm. So in the optimal estimation setting, what they're after is the posterior distribution of the true state given the radiance, and the only source of uncertainty that is included there or propagated is the observation error of the instrument epsilon. After much teeth gnashing over a period of something like 5 to 7 years, and with the help of Mike and John and Joachim and the OCO2 team, came to feel that a better view of that is that what we're after here is the posterior distribution of the true state given what we have derived as our point estimate X hat. One reason for doing this is that that posterior variance estimate is known to be too small for a whole variety of reasons, and we wanted to stay away from it. We wanted our uncertainty to be comprehensive rather than just propagate forward epsilon. Now, there are lots of other sources: the mismatch between F1 and F0, the mismatch of B1 to B0, non-Gaussianity, computational artifacts, all kinds of things. We can't even list them all. So we decided not to try to write them all down and then characterize them. We decided to do what I would call a top-down simulation experiment that we've dubbed an observing system uncertainty experiment, which is a riff on something that is known in the remote sensing world as an observing system simulation experiment, which bears a lot of similarities. So here in a nutshell is the basic idea. We want to, here's the top row in this picture is quite similar to the two flow charts I already showed. Let me get that out of the way if I can. Maybe I can do that. What we will do is we will generate a series of a synthetic truth ensemble that we're going to call XSIM in brackets here, right here. We are going to use a forward function to create synthetic noiseless radiances that correspond to the elements of that ensemble. We're going to add measurement error to it as we did before. We're also going to add something called a model discrepancy adjustment to account for the fact that we're using the same F1-B1 combination to generate these synthetic radiances as we are going to use in the retrieval part of the simulation experiment, because we only have that one. If we knew what the true one was, we wouldn't be doing this at all. So at the same time, it would be unfair to assume that F1-B1 used in the retrieval is the exact correct representation of what nature's doing. So what we came up with there was the notion that what we could do is we could corrupt our y's just a little bit, our y-sims a little bit, by adding an independent random draw from a distribution I'll call the model discrepancy distribution, which I probably don't have time to talk too much about, but there's a whole other story about how we estimated the parameters of that distribution. So in the end, we end up with a synthetic observation ensemble or a simulated observation ensemble called y-sim. We push that through the retrieval, we get out some x-hats, and now we have a bunch of pairs of x-sims paired with their corresponding x-hat sims. And now what we want to do is characterize that relationship. And we do it by fitting a Gaussian mixture model to that empirical ensemble, from which we can derive the conditional distribution of x-sim given x-hat sim. And in that way, we feel that if we did a good job generating our synthetic ensemble, and if all this works as intended, we believe what we've done is we've created a predictor of what the distribution of the true state would be given a new retrieval x-hat. So we just plug the new retrieval x-hat into the prediction equation for the point estimate for the covariance matrix. In this case, it'll just be a variance. And a mixture distribution. What we end up there is a Gaussian mixture regression model, which gives us the estimated posterior distribution of the state. So the big idea here is learn the parameters of the model from a simulation and then plug in the actual retrieval values. So here's a little bit, I won't dwell on this because I don't have time, but this basically just says what I said. If you're not familiar with the Gaussian mixture density, it's a fairly simple thing. A Gaussian mixture, a random variable that follows a Gaussian mixture is a random variable like V here, which isn't a draw from a single Gaussian. It is first a draw from a distribution that has specified probabilities adding up to 1 that puts a probability on each of the mixture components themselves. And then once you know the identity of the mixture component you're going to draw from, then you draw from it. And we denote that density as follows down at the bottom here. So we have the Gaussian mixture model with k components, and each component has a mean vector, a covariance matrix, and a weight or a mixing probability. And this, I've written this as in the vector case because we actually performed our operation on the full state vectors of OCO2, not simply on XCO2. We converted on XCO2 at the end, but we actually did this operation on the entire thing. So let me show you just a simple graphic of what we were doing here. I guess I'm going to show you that in a second. These are the well-known formulas for the component mean function and component covariance or regression covariance function by component, and for the mixing weights. So if I have a new observation U or a new retrieval U that is observed at U star, I can simply plug that into these formulas and build myself a Gaussian mixture model specific to that input, and then I can sample from it to simulate the posterior distribution for that footprint or for that retrieval. All right, I don't want to dwell on that. I wanted to get to this. Here's a really simple example in one dimension, or 2 dimensions rather. I have 2 variables, W, which you might think of as being like the state vector, and U, you might think of as being like the radiance. And I tried to make it kind of nasty, meaning nonlinear and heteroscedasiastic. The forward relation looks like that. The inverse relation is just swapping the axes. And when I swapped the axes, I also rescaled the U variable for some amount of convenience. Here, U is just a function of W. Now, if I were to try to I guess I should not have given away the story there. If I were to try to fit a single Gaussian to this, I wouldn't do a very good job. It would sort of be a football looking thing right about there, but it wouldn't be a very good description. If I fit the Gaussian mixture, I do much better. I'm getting much closer to looking at the data. So each component in principle can be a member of any of, each data point here in principle could be a member of any of the Gaussian components in this model, but obviously a component over here is going to be, let's say a component, let's say over here, a component here, a data point here is much likely to be more likely to be a member of the blue mixture component than the orange one way on the left. So I can fit those, I can fit the Gaussian mixture model. Each Gaussian component has a regression line, and each Gaussian component also has a covariance matrix, or in this case, just a variance, which is what I was trying to indicate with this little inset. And then for any new U star that you might give me over here, I can obviously track it up to each of the regression lines that at that location on the x-axis, and then I can weight those regression predictions, and I can do the same thing with the variance. So if I chose a point, let's say a new U down, down near this part of the distribution over here, I would expect its spread to be greater than if I chose one over here, and that's what I was trying to show here. So if I take those two slices out of that Gaussian mixture and plot them marginally, this is what I get. It looks pretty reasonable. So with that said, this is the exact same picture I showed you before, except I've made a few little changes here. Instead of simply using x hat sim as a regressor here, I'm going to use x hat sim and the column weighted XCO2 average that goes with that retrieved state vector. And it might sound duplicative because the you might say the CO2 column, the profile of CO2 concentrations in the column is already contained in x hat sim in the state vector. Why do I need also to include the column weighted average of those quantities if they're already in there? Well, the reason is that this pressure weighting function H actually is different from location to location. So the weighting of those components is different depending on where you are, and we wanted to pick that up. So we found that this actually provided a better predictor than not including that. We also ended up not including certain components of x hat sim as derived. The aerosol elements of the state vector, for example, were not doing a good job of helping us to predict our true states. So in the end, we ended up leaving them out. Okay, so what we actually did with OCO2 was we decided to create two different synthetic true state ensembles, one for land and one for ocean, because the physical properties of those two are quite different. And we struggled for quite a bit of time trying to decide how we would create these synthetic ensembles from which we would draw our ensemble of p-sims, or how would we create the distributions from which we would draw. It was necessary that those distributions be representative of what we think we would see in reality. And because the intended use of the OCO2 data is as input into flux inversion models, we decided to ask our friends in the flux inversion community what they would like. And they told us that there was an ongoing project where they had been called upon to split up the world this way for another reason, and told us we should use that. That's called the Transcom Regents, and I will show you, here they are. This nice map was made by John. And so the ocean regions were split up into 30 different zones, and the land was split up into 11 different zones, in which we felt that it was plausible to aggregate the actual the actual state vectors retrieved by OCO2 fit a Gaussian mixture to them. Now, this is a separate use of the Gaussian mixture from the one I was talking about a minute ago, but we would fit a multivariate Gaussian mixture model to these separate collections of actual OCO2 retrievals, draw from that and call that our truth, and then proceed with the experiment. And you may say that, boy, that sounds awfully circular to me. You're using the actual OCO2 data to provide a truth. And yeah, that's true. We are doing that. The thought process is that we think of this system as an estimator. And as we all learned in our statistics classes, estimators have properties like bias and variance. They have what you might call operating characteristics. And how can you assess what those operating characteristics are? In statistics, we often say, well, if the input is Gaussian, then the bias is this and the variance is that. If the input is something else, that estimator has different characteristics. So as long as our inputs are representative of what we believe the instrument will see when we go about applying this model to real retrievals, we assert that we are able to learn the system's characteristics with a simulation experiment this way. Now, you could actually use anything to generate these synthetic ensembles. You could use a physical model. I could interrogate my favorite flux inversion modeler or my favorite CO2 scientist and just ask them to come up with something. But the most complete, most comprehensive, and we believe most accurate representation of what we know about the carbon cycle is provided by the OCO2 data themselves, and that's why we did what we did. So we took 5,000 IID draws from the ensemble, from the distributions fitted for each of these zones. We piled them together, and then we fit our P of X given X hat model. And then we went to the places where there was actual ground measurements from a network called the Total Carbon Column Observing Network, TCON, and asked ourselves, well, are those actual TCON observations, which we will pretend are ground truth, even though they too come about from a retrieval of their own, where do those things sit within these distributions that we derived for the footprints that sit as close as we can get to those ground stations? So we did this analysis for 4 months from 2015, you can see them there. And while we were at it, we also decided to compare the result of what would happen if you took the Gaussian distribution specified by the operational mean and covariance matrix and evaluated that against the same criteria. And we decided that there would be two criteria, two metrics, which the one I just basically described, which is how centrally located within our distributions is the actual TCON value. And then because bias is an especially important characteristic to worry about in these data or these inferences, because these numbers are going to be fed into flux inversion models, we worry a lot about bias. So we decided we would also look about the bias of our distribution relative to that TCON value and the bias of the Gaussian approximation relative to the TCON value. Does anybody have questions at this point?
If anybody has questions, feel free to either use the chat box or the raise hand button to indicate that you have a question.
Hi, Amy. I have a quick question, if that's okay.
Hello, Shane.
Hi, Amy. Nice to see you. On slide 20, I'm trying to understand again, what was it? Can you explain again what is slide 20, and especially what are W and the X-axis?
Okay, so this is just a two-dimensional example where you might think of, let me go back to this one here, right? Think of W as the true state and U as the observation. And you know there's some sort of functional relationship between the true state and what you observe. You can flip that around to describe the inverse relation, which is on the right. Is that clear?
Yes.
Yeah.
Yes.
Okay. So here, what I'm saying is that if I were to try to describe that scatter plot on the left there with a single Gaussian ellipse, it wouldn't be a very good description of the data because it's not, number one, it's not linear. And number two, the variance changes depending on where you are. So this is sort of a cartoon version of the first order things that can go wrong when you try to approximate something that's not Gaussian with something that is Gaussian. So the different colored ellipses that are superimposed on that scatter plot are the component Gaussian distributions in a Gaussian mixture model that was fitted to these data. So not one Gaussian distribution to try to cover it, but I think it's 6 here, 6 different ones given by color. Does that make sense?
Okay, yeah, thank you very much. Yeah.
Okay, all right.
And I see that there's one more question from Chad. So Chad, would you like to ask your question?
Yeah, thanks. Could you just talk for a minute about the model discrepancy adjustment, how those parameters are chosen, how they're estimated, and also just about the idea of modeling that as being a random draw from a distribution and what effect that has on the uncertainty in the end.
Right, so I have some slides at the end about that. And I will be happy to take a deep dive here into this with you if you would like. I think I probably shouldn't take a lot of time here to discuss this now.
No, that's not necessary, but if you could just give a big overview of it.
Yeah, so the idea is what we would have really, model discrepancy in the statistics world is this. So where F0 and B0 are nature's true model, you might call it, and F1 and B1 are our model. And we have a noisy version of this, which is the radiance that the instrument sees. And we have this. This is easy to construct, except for the fact that I don't actually know what the true X is. I only have the retrieved X. But a little algebra and the ability to simulate can help us fix that, which is to say that this discrepancy, if you add and subtract something in here, you can break it out this way. And what it says is you can account, you wish you had real true X here, but you only have X hat. But you can adjust, you can account for that at least to some degree by using what you know from the simulation experiment. And the choice of a Gaussian was just for sheer convenience to see how this would work. There's probably a better way to do it than that, but we just wanted to give this a try. And I do think that it's kind of interesting, but of course it's you know, we're adding information here because we're using the simulation, we're using information from the simulation to try to get at it. The logic for doing it was that we know we would be too optimistic if we didn't do something to make the results a little bit worse. And the easiest way to do that was to add some corruption to the radiances add some corruption to the radiances. I can go into that in much greater depth with you at either at our next Clivar telecon or at another time. Is that okay?
No, that's great. Thanks.
Okay, so I'm going to go quick here. So here are the places, the TCON locations where these ground stations exist. So we're going to look at these stations. I'm going to show you, here's a result from 2 different locations, just 2 sort of, by my eyeball, rather representative examples of the kind of thing that happens. This is at the Lamont, Oklahoma site. The TCON value measured on, did I put it? I didn't put a day on here. I guess I didn't put a day because these are just examples, is indicated by the green line. the operationally retrieved Gaussian distribution with mean x hat and variance s hat is the blue distribution, and our simulated posterior distribution of the truth given the retrieved is the red one. So these are kind of just some examples. There are a lot of cases where you get this sort of thing, where the operational distribution is way too narrow, and because it's way too narrow, and even if it's just off a little bit, it's still not a good statistical description. The green line does not appear in the central portion of the blue. It does appear in the central portion of the red. There are also a lot of cases where everybody does well, everybody gets an A. There are some cases where nobody does well, everybody gets an F, like this one. And then there are some really interesting cases like this, where I would say the blue one isn't doing very well, and the red one is doing better, but it's really interesting that this is a bimodal distribution. It's not Gaussian. There's no guarantee that these red ones are Gaussian anyway. They may have heavy tails. We haven't actually gone in and quantified that, but it's pretty clear that in a case like this, where the distribution appears to be multimodal, you need something more than just the mean and the standard deviation, or the mean and the variance. So here are the metrics. I'm running out of time, so I won't go into great depth. Let us just say that all this is, metric number one is just the CDF value. If you took the distribution, here's the Gaussian distribution, or the Gaussian CDF value for a normal distribution with mean x hat and a variance s hat. What is the quantile at which the true t-con value falls? Here it's estimated from the simulated values. Metric two is what's the bias of the two different estimates of the mean of the mean of the distribution, either x hat in the case of the operational retrieval, or our simulated mean relative to the t-con value. And here's a very nice graphic that Joachim made that shows out of 944 footprints. And by the way, the footprints that we used here was, we did not do the usual thing that I've seen people do, is to draw some arbitrary size box around the t-con site and say anything in the box is a so-called match. And we'll compute our statistics based on the difference between anything in that box and the t-con value. We took the 1 kilometer footprint that actually contained the t-con site, and we used those. And there were 944 of those over those 4 months. And in looking at, this is just a scatter plot that shows the first metric on the x-axis and the second metric on the y-axis. And you see that on 63% of these 944 values, by our metric, we did better than the operational retrieval. Let's see, small is good in both cases, I believe. Joachim could probably remind me of what's going on here. We did worse in 25% of the cases. And I think, I'm not going to try to think that through in real time. Let me just go to this coverage table. This shows the different t-con sites, the different weeks, the proportion of the time that the t-con values fell within the 95th and 50th central portions of the distributions for the operational retrieval and our simulated, I'm sorry, for the operational uncertainty and the simulated uncertainty that we got. And red indicates that the number in this column is not 0.95 and the number of this column is not 0.50, and similarly here and here, and green indicates that it's at least that big. So here, of the 80 values, 80 footprints that we had at Bialystok, all of them fell within the 95th, and in fact, all of them fell within the central 50% of our distribution, whereas none of that was true for the Gaussian distribution reported by the retrieval algorithm. So you can see that we improved in a number of places here. There are some places where we didn't make the cut either. This Seduncula is a notoriously hard place because it's way far north and there are lots of problems there. Orleans is another mystery for us. This one almost works, but you can tell, I think some progress is made here. I think we can claim moral victory from this table. I'm not asserting that it is a universal validation of what we did, but based on what we've looked at, I think it looks pretty good. So I'm going to try to wind it up here. I'm going to put it back in the context of, I'm not going to do that because it'll take me as long as I have to go through that. So I'm not going to do that. I was going to put it back into the context of UQ in a more general terms, but we can talk about that offline. So the summary is just as you see here. The challenge was to develop something practical that would let us assign uncertainties to every footprint in our data set. We borrow a bit from some things we learned from the OCO2 team, who spent a lot of time doing bias correction by regressing the true state on the retrieved state. And we basically extended that to correct not just the bias, but to try to correct the whole distribution. And I think Mikhail was the person that noticed that that connection existed, and I wouldn't have noticed that if he hadn't pointed it out, so that's good. So I think we can say that the simulation-based confidence intervals are usually valid, but not always efficient. The operational confidence intervals are never valid, and I'm not sure if you even want to fool around with whether they're efficient, whether something efficient and wrong might not be a good thing. We did pretty well in this study, but we need to do more comprehensive examinations. And in fact, we're trying to gear up now to work with a new version of the OCO2 data. It is fairly computationally intensive in building the model, but once the model is built, it's pretty fast to apply. So I'm just going to show you my references and show you my acknowledgement and stop there.
Cool. Thank you very much, Amy, for the very, very interesting talk. I see we have a few questions. So let's start with Emil's question in the chat box, since he asked that a couple of minutes ago already. So Emil is asking, I can read the question here for you. So he's asking that when you were forming the likelihood and account for observational noise, do you typically consider any correlation structure in these noise errors? In the case of the OCO2 satellite, the instrumental noise might be independent, but do you assume that the observational errors are independent from one pixel to another?
I think there's two different answers to that, one of which I'm going to defer to John and Joachim about how we simulated that error term. The team tends to treat epsilon as a diagonal matrix and not account for cross-channel errors. But epsilon is really functioning in that setting. Epsilon, in the model, epsilon is more than just sensor noise. Or you could argue that it's just taking up everything that's not in F. And so we've actually started an activity to try to tear that apart and figure out what components might be coming from model discrepancy, what components might be coming from calibration error, what components might be coming from sensor noise, and so on. That's on a different track. But in the simulation experiment, I'm going to ask John or Joachim to respond to that about how we did that simulation, if we used diagonal noise or not. I hope one of them are out there.
Hi, Amy. This is John. Yeah. So in a simulation, what actually ends up happening is, formally, the epsilon term is the covariance of the epsilon term is diagonal, as it is assumed in the retrieval. But as you discussed earlier, the model discrepancy is a stochastic term that has not only non-zero mean, but it also has correlation across channels. So in terms of our synthetic radiances, then that gets passed through to the synthetic radiances, and there's a bit of cross-channel correlation in the end there.
Right. So that is one source of uncertainty that we want to account for, and it's accounted for by the fact that our simulated truth has that cross-channel uncertainty via the model discrepancy, but the retrieval does not.
Cool. Yeah, thank you very much. Hopefully that addresses Emil's question. I see there's one more question from Grace Chiu, who indicated in the chat box that she has a question. Would you like to unmute and ask your question, please?
Yeah, thanks, Mikhail. Amy, thank you so much for the presentation. I thought it was really refreshing that your state space modeling framework considered both the forward UQ and backward UQ, because thus far, a lot of the state space models that I've encountered only consider the forward UQ. And that's partly why personally for my work, I never really employed state space modeling. And I prefer Bayesian melding because Bayesian melding, the framework itself, has the built-in forward and backward UQ when you propose your priors. So I was wondering if your team has considered using Bayesian melding, and if not, would you maybe look into it?
I have to confess that I don't know very much about Bayesian melding. It came up some years back in the context of some data fusion work we were doing as an alternative to data fusion. I would have to look into it a little bit more. The only thing that would prohibit it, well, would be computational expense and whether we would have to get into the guts of the retrieval in some way, in a way that we can't. John, do you know what Bayesian melding is? Do you have an opinion?
I'm not very familiar either, but yeah, it's something that we could look at some point,
Yeah.
I think.
The name Montse Fuentes comes to mind. Am I right about that?
That's right. So Montse, I think it was her postdoc work. But since then, there has been a lot of advancement. So I would love to chat with your team if there's any interest.
Yeah, that would be great. Mikhail knows how to find us.
Thanks.
That would be terrific. Thank you.